This presentation will focus on sedimentary processes, which includes the topics of weathering, erosion, and sedimentary rocks. These are our learning objectives for this chapter. We will discuss the different forms of weathering and erosion, the difference between the two. We'll talk about the types of sedimentary rocks that exist and especially differentiate the two main categories of sedimentary rocks. And we'll also have a discussion on important sedimentary structures as well as looking at sedimentary environments or depositional environments where sedimentary rocks form. We can't talk about sedimentary rocks without first talking about water, and that is because water plays a very important role in the formation of most sedimentary rocks, including chemical sedimentary rocks and clastic sedimentary rocks. So one of the very special things about water is its polarity. So the water molecule basically consists of two hydrogen atoms and one oxygen atom. You probably know this, H2O, right? But these two hydrogen atoms are covalently bonded to that one oxygen atom, and their arrangement is important, right? The geometry that they form is important here. The two hydrogen atoms are separated by an angle of about 105 degrees, and both are located on one side of the hydrogen atom. This atomic arrangement, what you get with this atomic arrangement is that you have positively charged hydrogens on one side and negatively charged oxygen on the other side. And this is what gives water a property called polarity, which you've probably heard that term used to describe a magnet or a battery, right? It's the same thing. It has polarity. And so that molecule's positive negative architecture or geometry leads to a whole suite of characteristics and properties. So polarity, having polarity, allows the water molecules to stick to other surfaces. And when water sticks to a surface, we call that adhesion. Water is also attracted to itself, and that property is called cohesion, which leads to an observation that you've probably taken for granted, but seeing a droplet, right? An actual droplet, that's the water. Cohesion is responsible for that property. So cohesion creates surface tension, which is something that various insects use to walk on water by distributing their weight across the surface. So that cohesion allows for the formation of droplets. Also, because of that cohesion or that property of water being attracted to itself, leads to another very interesting and rare property, which is that the liquid form of water is more dense than the solid form. So typically, with most natural materials, the solid or frozen form will be denser than the liquid form, but that is not true for water. The polarity of water, because of the polarity of water, when you have multiple hydrogen molecules coming together and bonding, they don't bond covalently. The atoms within the molecule bond covalently, but the molecules among themselves, they bond using a bond called hydrogen bonding, which is not a very strong, it's considered one of the weaker bonds. And so this polarity of water creates that special kind of weak bonding, hydrogen bonding, and so the hydrogen bonds allow the molecule in the water to sit close together. And what's interesting is that water is actually the most dense at 4 degrees Celsius, and it's less dense above and below that temperature. So as the water solidifies into ice, the molecules must move apart in order to fit into the crystal lattice or the crystal geometry. And this causes the water to expand and become less dense as it cools. So because of this, ice floats. Ice will float in your cup of water. And water that is 4 degrees Celsius will actually sink, will actually drop, it will become more dense. So this is actually what keeps or what helps drive ocean currents, right? So that 4 degrees Celsius water that sinks keeps the ocean liquid and prevents them from freezing solid from the bottom up. So this is a very unique property of water, and it is also what helps keeps the earth and the planet habitable. Another interesting about water is that it is a universal solvent, meaning it dissolves more substances than any other commonly found liquid. The water molecules use polarity and uses its polarity and the hydrogen bonds to basically pry or remove ions away from the crystal lattice of things that it encounters. So water it's so powerful of a solvent, it can dissolve even the strongest rocks and minerals given enough time. The last really interesting thing about water, other than supporting life, or I guess this would kind of go in hand with it being essential for life, but water is really special because it remains liquid over over a very large temperature range. And this is in part a result of cohesion. The hydrogen bonding also permits water to absorb high amounts of energy before turning into gas. And so this wide range across which water exists as a liquid, basically 100 degrees Celsius, so from 0 degrees Celsius to 4 degrees Celsius, it's a really wide range, and it's not seen in a lot of different natural liquids. So without this high boiling point, water on Earth would really be confined to narrow temperate zones on Earth, but instead that's not what we see. We see on Earth that water is found from pole to pole. And so it's really the only substance that we see exists in all 3 phases on the Earth's surface. Now we're going to discuss weathering and erosion, and over the next several slides I'm going to talk about each of the different types of mechanical weathering and chemical weathering. What you will see, a term you will see come up repeatedly is the term bedrock, and this refers to the solid rock that makes up the Earth's outer crust. And typically it's referring to continental crust. And so weathering is the process that takes that bedrock and breaks it into smaller pieces called sediment. Now, erosion is the mechanical process, which is usually driven by water, wind, gravity, or ice that transports sediment. So it's a mechanical process that transports sediment from the place of weathering. Okay, so these 2 things usually go hand in hand, weathering and erosion, but you need both to form sedimentary rocks. Now, liquid water is really the main agent in erosion. Gravity and mass wasting processes, which we'll talk about in a later chapter, they can also move rocks and sediment to new locations as well. And then gravity and ice as well in the form of glaciers can move very large fragments as well as fine sediment. But I mean, typically with ice or glaciers, the movement, the transportation is going to be a bit limited. Like water can bring sediment very, very far, but ice can only bring, or glaciers can only bring sediment as far as the ice can exist, right? So it can't, if it's an alpine, if it's on at a high elevation, and that glacier can only extend down so far down the mountain. But moving on. So erosion resistance is very important in the creation of distinctive geological features. And those would be examples of things that you would see, like if you drove out west, the cliffs of the Grand Canyon, or certain rock faces or outcrops that are still standing, either, in certain national parks, or, driving through kind of the west, like the southwest especially. Um, a lot of these geologic features that you see are because those particular features were resistant to erosion. So, Bryce Canyon would be an example of that. Arches, a lot of national parks have great examples of, you know, really neat looking, distinctive geologic features. The first kind of mechanical weathering that we're going to talk about is pressure expansion. And note that mechanical weathering is any type of weathering that physically breaks the bedrock into smaller pieces. And so the usual agents of mechanical weathering are pressure, temperature, freezing, thawing, plant or animal activity, and salt evaporation. So those are the main agents, right? And so now I'm going to talk about pressure expansion. So when you have a bedrock and it's buried deep within the earth, it experiences high pressure and temperature. But when that bedrock is uplifted, meaning it rises higher in the earth's crust, either because of plate tectonics or because of erosion, right? When that uplift and erosion brings the bedrock closer to the surface, there's less pressure on top of that rock, and there's a lower temperature as well that it is experiencing. Like the temperature will drop slowly as it's rising, but still it's a drop in temperature and a drop in pressure. And this pressure drop causes the rock to rapidly expand and crack as a result. And so this is called pressure expansion. And you get something called sheeting or exfoliation, and that's when the rock surface kind of splays off in layers. Um, kind of, it almost looks like shingles coming off, or it can like slide off of a surface, an exposed surface of a rock formation. And then there's a specific type called spheroidal weathering. This is a type of exfoliation that produces round features, and it's typically caused when you have chemical weathering involved as well. Frost wedging or ice wedging kind of describes what it sounds like. It uses the power of ice, expanding ice. So this is where one of those really weird or interesting or unique properties of water has an important role, because as we talked a few slides ago, water expands when it freezes, and that's kind of the driving force causing frost wedging. So it uses the power of expanding ice to break apart the rocks. And the water basically works its way into the cracks and voids and the crevices, and it freezes and it cracks some more. So as you have a cycle of, maybe there's a weak crack, water gets in, it freezes, splits it open, and it kind of just continues, right? The water keeps seeping into cracks that the previous cycle of frosting created. Now, these cycles don't necessarily have to be seasonal. These cycles of freezing and melting can actually happen on a daily occurrence, if this is happening in an area that experiences very large temperature fluctuations between day and night. Root wedging is a lot like frost wedging. It happens when the roots of a plant basically like work their way into cracks, and in doing so they can pry apart the bedrock as it grows, as the roots get bigger. Some of these roots can actually become fossilized, and the term for that is a rhizolith. And here in this example, it's showing you, asphalt or pavement, but this has been observed in the rock record. The last type of mechanical weathering we'll talk about is salt expansion, which is similar to frost wedging, but this type occurs in areas where there is high evaporation or it's near a marine environment. So areas that experience an increase or an influx of salts and experiences salt precipitation. So you have evaporation that causes salts to precipitate out of solution. So when it precipitates, that means a solid comes out of a liquid solution. And you'll have salts precipitating, they'll grow and expand into the cracks in a rock or the bedrock. And this salt expansion is one of the causes for a texture that you get in a rock called taphony, and it basically describes a series of holes in a rock that look like this picture here. And anytime that you are creating holes, cracks, you're creating additional surfaces. And with the additional surface area that is exposed, you increase a rock's susceptibility to weathering. So as this process continues, weathering will only accelerate. Now remember, chemical weathering is the breakdown of mineral material through chemical methods like dissolution and oxidation. And chemical weathering is really the main type of weathering in warm, humid environments. It occurs when water, oxygen, and other reactants chemically break down a mineral or the mineral composition, the mineral components of a bedrock, and basically dissolve them into the water. And they do that by dissolving the minerals and breaking down those minerals into their soluble ions. Now, once those ions are dissolved in the solution, that water moves away, right? And those ions are transported to a different location. So they're removed. If the water was just sitting there, I guess there would be the opportunity for things to recrystallize in place. But typically what happens is that water is not only, dissolving things, it is removing it from the system. It's removing those ions from the system. And when you have higher temperatures, that process accelerates. Now, chemical and mechanical weathering, it's not usually one or the other. They work hand in hand. Chemical weathering really only affects the surface of the rock. Like we were talking about physical weathering, right? You have these cracks in the rock, the water can get in or roots can get in and break things up, right? Like it can penetrate, physical weathering can penetrate the rock, but chemical weathering really only works on the surface of the water. So unless the surface is exposed, then unless you have extra surface area, then only the outside of the bedrock basically is going to dissolve or be susceptible to chemical weathering. But they work hand in hand because when you have mechanical weathering penetrating the rock, breaking the rock into smaller pieces, by breaking the rock, you increase the surface area. So that's what these cubes here are trying to show you. Like volumetrically, I think these are all supposed to be equal, but you see how this cube here has these 6 surfaces where it can be chemically weathered, right? Like coming into contact with water. But when you break this down into smaller pieces, you get much larger, you get an increase in the surface area, and therefore you're increasing the rate of chemical weathering. So there are two other chemical weathering reactions, hydrolysis and dissolution. Now, an important part of these two, hydrolysis and dissolution, is carbonic acid. Carbonic acid is H2CO3. This forms when carbon dioxide dissolves in water. And this happens naturally. It happens in the atmosphere, in the clouds. It's the reason why precipitation is a little more acidic. Okay, but carbonic acid is very important for hydrolysis, which we'll talk about first. Now, hydrolysis can occur two ways. One way is when the water molecules ionize or break apart into the positively charged hydrogen plus 1 and the negatively charged oxide OH, which has a negative 1 charge, and it replaces mineral cations in the crystal lattice. The other way that hydrolysis occurs is that the carbonic acid molecules react directly with minerals, especially minerals that have silicon and aluminum, so feldspars. And so they react directly with certain minerals to form molecules of what are known as clay minerals. So they basically create different minerals that weren't there before. And hydrolysis is the main process that breaks down silicate rock and creates clay minerals. Now, clay minerals are platy silicates, also called phyllosilicates, and they are structurally similar to micas. They are the main components of very fine-grained sediment and fine-grained rock, which we'll talk about later in this presentation. Now, the dissolved substances that may remain in the water can eventually precipitate out into chemical sedimentary rocks. So dissolution is a hydrolysis reaction, and it basically dissolves minerals in the bedrock and leaves the ions in the solution. The presence of acid accelerates this dissolution. So whether the acid is natural or artificial, or maybe as the result of a biological activity like organisms, because of organisms like lichen or bacteria releasing organic acids, the presence of acid will increase the rate of dissolution, as well as increase temperatures and increase humidity. And also, when we're talking about dissolution, so there's the Goldick dissolution series, which basically it describes the rate not as discretely as the Bowen's reaction series, but in general, it suggests that the chemical weathering rates that are related to the crystallization rankings, basically, of the Bowen's reaction series. So the minerals at the top of the Bowen's reaction series, they crystallize under very high temperatures, very high pressures, but they chemically weather at faster rates, right? So the idea behind the Goldick dissolution series is that minerals that find themselves in environments that are the most dissimilar or most unlike their environment of crystallization, they will dissolve, or they will weather more readily. So what that means is that those minerals at the top of the Bowen's reaction series, your mafic minerals, olivine, pyroxene, amphiboles, those mafic high crystallization point minerals will weather more rapidly and more readily and more completely. Contrast that to the feldspars and the quartz, the felsic minerals, which crystallize at a lower temperature. These tend to be more resistant to chemical weathering. The last type of chemical weathering we'll talk about is oxidation. And oxidation is the chemical reaction that causes rust in metallic iron. This occurs when iron atoms in a mineral bond with oxygen, and any mineral that contains iron can be oxidized. So when you have a mineral that has iron that's oxidized, we call those iron oxides. Three commonly found minerals that are produced by iron oxidation are called hematite, goethite, and limonite. And these are examples of common iron oxides. And these iron oxides can coat and bind mineral grains together. So they can coat these sedimentary grains, and when they help bind the grains together, they act as a cement, and that process is called cementation. Because the grains have this coating, they often give the rocks a dominant color. And so the colors of the rocks in the Colorado Plateau are a result of this process. So if you've been to Zion or Arches or Grand Canyon, the reds, the yellows, the browns that you see are because of these iron oxides. Erosion is the physical process, the mechanical process of removing sediment away from the place where the sediment was created or where the weathering occurred. Liquid water is one of the main agents of erosion. It can be, a very powerful erosive agent. But, sometimes if you don't have a high volume of water, it can be a slow process. So the rate at which erosion occurs can vary widely, depending on the flow rate or the amount of water that you have. And putting aside that solid water, so ice, glaciers are incredibly erosive. Without really having to move very far or travel very far, they can be very erosive. But the opposite of being susceptible to erosion would be being resistant to erosion. And this is an important feature that distinctive geological features require. So here's a picture of a hoodoo in Moab, in Utah, and this is the remnants of rock layers that were, or portions of rock layers that were resistant to erosion. In most geologic subdisciplines, we don't spend too much time talking about soil, or at least not current soil. We might interpret past soils that are recorded in the geologic record. So we'll spend a couple slides here talking about soil here. So what is soil? It's a combination of organic material as well as minerals, sediment, water, and air. And you can really think of soil as a transition between the atmosphere and geosphere, but also the biosphere and the geosphere. And most soils are made when weathering rock breaks down the bedrock and turns it into sediment, and that's kind of the starting point is having sediment. If erosion does not remove that sediment in a significant way, meaning the sediments accumulate, then organisms can basically make use of the minerals contained within the sediments. And so these organisms can turn minerals, water, and gases into organic substances that later contribute and add to the soil. Soil is very important for organic components necessary for plants, animals, and microorganisms to live. the organic component is very important. And the organic portion of soil is called humus. It's a rich source of bioavailable nitrogen. And so this is very key. The presence of nitrogen is very important here because the nitrogen is, it's very common in the atmosphere. It's an important element with for life. Like we have nitrogen in our bodies, right? Um, so but it exists in a form that most life forms are not able to use. Like um, the way it exists in the atmosphere, for example, like we're not able to extract atmospheric nitrogen and use it in a way that our biology needs, right? Like we're not able to do that. We can extract oxygen from the atmosphere and use it, but we're not able to extract nitrogen from the atmosphere that way. So that's where special bacteria come in. Special bacteria that's found only in soil that are necessary to provide most of the nitrogen compounds that are bioavailable to us and other life forms. And these special type of bacteria, we refer to them as nitrogen fixing bacteria. So what they do is they absorb nitrogen from the atmosphere, which we can't do, and they convert it into the nitrogen compounds. These compounds are absorbed by plants and are later used to make DNA, amino acids, important parts that life forms need. And so animals obtain this bioavailable nitrogen by eating the plants, and this is the source of most of the nitrogen that's used by life or, organic matter. Now, because this organic component of soil is so important, oftentimes when you might hear a scientist refer to poor soil or rich soil, what is that poor or rich referring to? It's typically it's typically referring to the amount of organic material within the soil. So a poor soil will have little organic material, which would impact the soil's productivity. Few other things about soil. In areas that are sloped, you are not going to have as thick of a soil layer as opposed to areas that are flatter where soils can, accumulate. And to go back to the sloped areas, not just because a slope exists will you have a decreased accumulation of soil. It is also the fact that you get more erosion when you have a slope. So water will travel down that surface, and when you have water under the influence of gravity, you get increased erosion. So typically, it's not just the fact that the surface is sloped that you get, thinner layers of soil, but it's the fact that those sloped surfaces tend to be more susceptible to erosion. And so not only does the content, so is it rich, is it poor in organic matter, but the thickness of the soil, these are all things that affect the quality of the soil, the chemistry of the soil that's available, and of course, its location on Earth. So temperature, precipitation, seasons, basically the climate are also going to impact your soil formation. So when you're looking at the soil in more detail, it can actually be broken down into several layers. And typically closer to the surface, you have more organic rich material. And as you go down further and toward the bedrock, you become, less enriched in organic material. Each layer has, a name, a soil horizon letter, distinctive kind of nickname. So layer O, organic, A is near the surface, B is your subsoil, C would be your substratum, and by the time you get to R, you're looking at the bedrock. Now, soil is in and of itself an important resource. I mean, it's essential for life on our planet, for, agriculture. So it's an important resource to protect and take care of, and um, there's a lot of mismanagement that goes on with how we treat our soils, what we put into our soils. Um, yeah, so in the textbook, it references the dust storm, and the famous Dust Bowl disaster in the 1930s, that came about from overdevelopment of prairie lands and kind of mismanagement of the soil. And so it's not a finite resource, and it's certainly something that we need to be aware of, as a society, how we are, managing our soils and managing agricultural practices rather. Okay, now we get to talk about sedimentary rocks. Sedimentary rocks, there are basically two types. You have clastic or detrital sedimentary rocks and chemical sedimentary rocks. Your clastic rocks are formed from clasts or detritus, which basically just means pieces of other pre-existing rock or sediment. And then your chemical rocks form from mineral precipitation. Because of this, classic rocks and chemical rocks are classified a bit differently. Classic rocks are classified by their grain size, their shape, and their sorting, and chemical rocks are classified by their mineral composition. How we go from sediment to sedimentary rock is through a process called lithification, which turns your loose sediment grains that were created by weathering, erosion, and transportation into a clastic sedimentary rock. And there are three main steps for this. There's deposition, which happens when friction and gravity overcome the forces driving sediment transport. What does that mean? It means that the sediments stop moving. The forces that were moving the sediment are no longer strong enough to keep moving the sediment, and the sediment fall out of suspension. So the sediments settle down. They can't be moved any further. So they settle, they deposit. Then follow that with compaction. So over time, you have increased deposition, right? Sediments continue to accumulate on top of each other. And over time, you compact that sediment that has accumulated. Now, this compaction occurs through continued accumulation, and as it's happening, it's squeezing the grains together, and that process is also removing water. So the mechanical compaction is also aided by weak forces between the smaller grains of sediment. And then as that process is happening in a lot of areas, you typically have groundwater that is carrying dissolved material that can act as cements. Right? So the last step is cementation, which is like what it sounds like. It's the process of cementing mineral or sediment grains together, gluing them together. And so minerals like calcite, oxides, amorphous silica that are carried in the groundwater can help with cementing the sediments together. Now, diagenesis is like an extension of lithification. So it's an accompanying process to lithification, and it's a form of like low grade metamorphism. During diagenesis, the sediments are chemically altered by heat, slightly increased heat and pressure. And so you chemically alter the sediments. Diagenesis also further reduces the pore space. So the pore space within a sedimentary rock is going to be the space in the rock that is not taken up by any other sediment. So it's like they're like void spaces, pore space, or open volume. And so the process of cementation and compaction and ultimately lithification, it's all related to diagenesis, but they're not exactly the same. So, think of diagenesis as like a more broad term for all of the physical, chemical, biological changes that a sediment undergoes after deposition, whereas lithification is a specific process kind of within diagenesis, and it turns that, unconsolidated sediment into a sedimentary rock. So lithification involves that deposition, compaction, cementation, but diagenesis includes the other changes like mineral dissolution that can happen from the groundwater, or alteration that can happen either during or after lithification itself. Clastic rocks or detrital sedimentary rocks are classified first and foremost by their sediment grain size, which here is a very common scale that is used, the Wentworth scale, and you can see that it's quite detailed. And it just depends on what you're doing and what area of geology you're focusing on, whether these details, like this level of information, matters. So I'll give you an example. When I did my field work for my field course, the primary objective, of course, was to become familiar with different lithologies in the real world, but ultimately the end product that I would have to turn in was a geological structural reconstruction of the area that I was surveying. So understanding the structural geology was paramount, was like kind of the most important thing for me to focus on. So for certain assignments where that was my focus, I wouldn't necessarily worry about where exactly on the Wentworth scale the sediments I came across, or the rock units I came across, laid on, right? But when I worked in the oil industry and I had to look at logs and cores of different sedimentary rocks and try to find potential reservoirs or find where source rock was, then it became very important for me to know exactly the specific grain sizes across a certain area, across different depths. And so, not every geologist for every project will necessarily have to focus on, knowing exactly the precise grain size. It really just depends on what you're working on as a geologist. But this is like a standard kind of, widely used scale, the Wentworth scale. And the general terms that we use for size to describe sediment are clay, silt, sand, pebble, and then you have cobbles and boulders. And so you see these terms here, right? And then within each one, with the exception of clay, you have very fine silt, medium silt, coarse silt. Then you have sand, very fine sand, medium sand, coarse sand, very coarse. Pebbles, you have very fine pebbles, very fine sand. When you're out on the field though, and you don't have this scale next to you and you're taking your notes, you might call it a very coarse sand and someone else might call it a very fine pebble, right? Like these are, very small kind of differences here. So again, kind of depends on what your focus is. But in general, what you have here, what you see here are the smallest grains are at the bottom of this scale, and then the larger grains are, and then the grains get larger as you move up the scale. Another term that is used to describe sedimentary rocks is the sorting. So the sorting describes the range of grain sizes that you see within a sedimentary rock. So the term well sorted will describe a rock that has a narrow range of grain sizes, whereas poorly sorted will describe a rock that has a wide range of grains. So if we're looking at this one here, we would say this one is well sorted, and this one here is poorly sorted. So if you have a wide range, like you have a lot of different grain sizes, that's poorly sorted. You have, grain sizes that are generally pretty similar, very close, well sorted. Then you have rounding, which is also used to describe the grains themselves. And rounding is created when the angular corners of rag fragments are removed from a piece of sediment due to transportation, basically, due to the abrasion during transportation. So rounding, you get increased rounding the further the grain moves away from its source, because it's bumping into a lot of different things, and its sharp edges are becoming duller and duller. So a well-rounded sediment grain, or a rock with well-rounded sediment grains, are defined as being free of all sharp edges. So if it's well-rounded, it would have no round edges here. So here it's just giving you from left to right, you're moving from more angular sediment to more rounded sediment. And what you see here from the top down is sphericity. So basically the roundness of the grains. Composition is also used to describe sedimentary rocks. And of course, it describes the mineral composition and the mineral components of the sediments in the sedimentary rock. For sedimentary rocks, this composition is going to be influenced, of course, by the local geology, but also hydrology, so the presence of water and the impact of that water has had. With the exception of clay, most sediment components are actually a bit easier to determine visually than, say, maybe some, wider variety of like igneous rocks, and that's because the most commonly found sediment mineral is quartz, and it's quartz for a reason. Quartz is very common in sedimentary rocks because it has a low chemical reactivity and it has a very high hardness, which come together to make it pretty resistant to weathering. And so it is very common in continental bedrock, as well as feldspars, which are not as resistant as quartz, but still fairly resistant to weathering. Now, when you think about a typical beach that you go to, right, you're looking at sediments that are, light colored, a lot of sand, or I'm sorry, a lot of quartz in the sand, right? That sand, to get to be that well sorted, to get to be that spheroidal, and to get to be that well-rounded, had to travel a long distance, right? Because we know quartz is very resistant to weathering. So if we see well sorting, well-rounded, we know that those sediments traveled a long way. Now, when you think about, if you've ever been to Hawaii, if you've ever seen the black sand beaches in Hawaii, they're very unusual because you have sand grains, but they're not made of quartz. They're broken down basalt and olivine. And the reason that you have these black sands there is because that basalt and olivine, they break down much more easily. So they're able to become well sorted, well rounded over a much shorter distance and over a shorter period of time than quartz would, for example. So, if you had a beach next to a more felsic mountain, right, like right next to it, you will not see small sand size grains. You would see much bigger boulders and pebbles, right? If you were as close as the Hawaiian beaches are to the Hawaiian volcanoes. And that reminds me, another thing I didn't mention in the slide about sediment size, the term sand refers to the sand that you are likely familiar with, the sand that you see at the beach, but it also refers to a grain size. So sand, like sandstone, for example, is made of sand-sized particles or sand-sized sediments. The term provenance refers to the original source, like where did this sediment or sedimentary rock come from? And provenance is basically determined by looking at the mineral composition, looking at fossils that are present, looking at texture, looking at sorting and rounding to figure out the original source of the sediment or the sediment in the sedimentary rock. And geologists, we use provenance to help put together tectonic histories, and to help, reconstruct paleogeographic settings, like figure out like paleogeographic formations and understanding how the Earth's like continents moved, and basically it helps us guide and helps us reconstruct past configurations of our continents. So what are these clastic rocks called? If it is a coarse-grained rock, meaning that the clasts are larger than sand and it contains a matrix or a ground mass, like a background with smaller grains, we call that coarse-grained rocks. And then two main types of very coarse-grained rocks would be conglomerate and breccia. It's a conglomerate if the clasts are rounded, especially the bigger class. And it's a breccia if the clasts are more angular. But both conglomerate and breccia are going to be your coarse-grained rocks, and they are both poorly sorted. The distinction between the two is that one has rounded and the other has angular clasts. Now for your medium-sized grains, sandstone. It's going to be sandstone, your sand-sized grains. It'll also be referred to as arenite if it's, very well sorted. Quartz sandstone if it's predominantly quartz. Arkose if the sand-sized grains are predominantly feldspar. And also greywacke if there's a lot of sand, like sand grains in there, but they're muddy or have like a lithic matrix. With your fine-grained rocks, so these are going to be rocks that have a grain size that are smaller than sand. So they're either going to be in that classification chart, they're going to be either silt or clay. And we refer to rocks that are made from these grain sizes as mudstone, shale, siltstone, and claystone. Your chemical sedimentary rocks are formed by processes that are not directly involved with mechanical weathering and erosion. So chemical weathering, it can contribute to the dissolved materials in the water that ultimately form these rocks. You have biochemical and organic sediments. They can be clastic in the sense that they deposit and accumulate, get buried and lithified in a similar way as, the clastic rocks do. But the key distinction is um, that they were chemically produced. So we would still refer to them as chemical sedimentary rocks, like coquina being an example of one. Your inorganic chemical sedimentary rocks are when you have minerals that precipitate out of an aqueous solution, which is usually due to water evaporation. You can also have it in a situation not necessarily because of water evaporation, but because of supersaturation. So you get really high amounts of a certain dissolved mineral, and then the liquid, the water just can't hold that anymore in solution, and it precipitates out. One really interesting rock that is observed in the geologic record, but we don't have a current analog for it, is the banded iron formations, or banded iron formation deposits. Sometimes geologists will just call them BIFs, BIFs. So BIF deposits were commonly formed early in Earth's history. And this is a type of chemical sedimentary rock, but it no longer exists. We don't have any observable environment at the surface where these formations are created. And so what you had was oxygenation of the atmosphere and the oceans caused free iron ions to become oxidized. And when they became oxidized, it precipitated out of solution, forming these deposits. So the iron oxides were deposited, and usually in alternating bands between iron and chert. And chert is another one. It's one of my favorite rocks. I think it's really cool, has a really cool, smooth texture, and it's also a chemical sedimentary rock, but it is produced from silica that has been produced. So we see silica, in igneous rocks and granites. We see it in sandstones and the grains, but we also see it in chemical sedimentary rocks when it precipitates out of solution. And typically you have water deep underground that's subjected to high pressure and temperature, and it keeps the silica dissolved in this aqueous solution. And then as the groundwater rises toward the surface, or it can rise slowly or emerge abruptly, but it either way precipitates out and forms these really neat rocks called chert. Oolites are really interesting. They're a type of limestone, which a lot of limestone comes from the uh, precipitation or the accumulation of organic calcite, but oolites form when it's an inorganic process, and it forms very similar to like evaporite deposition. So you have precipitation out of water. So when water becomes oversaturated with calcite, the mineral precipitates out, and it typically will precipitate out around a nucleus. So it'll need like a surface to precipitate on, and typically that surface will be a sand grain or a shell fragment or something small. And so you end up getting precipitation around an existing grain, and so they look like little spheres, and we call those ooids. And so as evaporation continues, the ooids continue building these concentric layers of calcite as they, roll around in gentle currents, kind of maintaining that shape. Biochemical sedimentary rocks are similar to chemical sedimentary rocks, except they form from ions dissolved in solution. So biochemical sedimentary rocks rely on biological processes to extract materials out of the water, dissolved materials out of the water. This process, basically can form limestone. So limestone's a really interesting one because you can get it you can have limestone a number of different ways. And what is limestone? Limestone is just a rock, a sedimentary rock that is mostly made up of calcite. And calcite can um, precipitate, can crystallize in a number of different ways. And so, biochemically, it can precipitate and form the rock limestone. You can also get other rocks that are similar to limestone, like dolomite, which just has some magnesium in addition to calcium. But limestone can also occur when you have the preservation of a coral reef. So basically, an entire coral reef and its ecosystem, it builds itself on as it builds itself, it creates these calcite deposits, right? Like the hard parts of a coral reef are calcite. The living parts are, the creatures that live there, the aquatic animals that make up the reef. But when those die off, what's left is the calcite that was precipitated out, and that can be buried, undergo diagenesis, and form limestone. There is also a type of limestone or a rock called coquina, and this is one that can form on beach sands. But it's a really cool rock because it is basically the accumulation of shells, like animal shells, and they're not necessarily broken down so much that you can't tell what it is anymore. Like you look at a coquina and you can see individual shells, but they've been cemented together. Now, organic rocks like coal, for example, they're a bit unique. They're considered sedimentary, but they're not necessarily derived from sediment. However, they do undergo a similar process of diagenesis or lithification, right? There's deposition, there's burial, there's compaction, and lithification. But what's lithified is predominantly organic material. So for coals, you often have the preservation of like plant material, or think of like the all of the organic material that you would see in a lush swamp or bayou, like that can get buried and deposited and eventually become coal. Now, sedimentary structures look at, you kind of take a step back a little bit and you're not just looking at the grains anymore, the sediments. You're looking at visible textures and arrangements of the sediment within the rock. And we use these structures to help interpret the processes that made up the rock, meaning try to understand the environment in which they formed. For example, bedding planes, which is probably the most basic sedimentary structure. The bedding plane is the plane that separates the layers or the strata in sedimentary rock, but also a volcanic rock. The same terms apply, bedding planes or strata. And so what you have is they are features that are visible in exposed outcrops, and each bedding plane indicates a change in the sediment deposition conditions, right? Because that basically defines a boundary. If you have no change in the environment and just steady accumulation, then you are going to end up with bedding planes that are very thick. But if you see layers, like thin, stacking layers, then the fact that you are seeing different layers tells you that there was a change. And the change doesn't have to be significant. It just has to be subtle enough to change the pace of accumulation and deposition. And when you're looking at each layer, so each layer we call each one a bed or a stratum. and it's a bed or stratum is the most basic unit of stratigraphy. So stratigraphy is the study of sedimentary layers or sedimentary layering. So it's a subdiscipline of geology, stratigraphy. And so your bed thickness can, indicate a lot about the depositional environment, the quantity, the timing, um, and any changes in that. Another type of sedimentary structure would be called graded bedding. So here you're looking at a series of strata, a series of layers, and typically you have increasing coarse or fine-grained sediments. So your graded bedding, they often occur in environments where the energy that's moving or carrying sediment changes, and typically in environments where the energy decreases. So a very common example of a graded bedding like sequence is called the Boma sequence. This is observed in a rock type, in a classic rock called a turbidite. So Boma sequences are formed offshore, usually on continental slopes. And what you have is you basically have, like, if you can think of a like a mudslide on the surface, you kind of have that equivalent, but underwater on the continental slope. So you get these underwater flows of sediment. And so as you can imagine, you have, it's a turbulent flow. Like everything's not, like when you have, a landslide or a mudslide, like you have stuff all mixed up, worked up. So that's what's happening here underwater offshore, right? You get this turbulent flow and you get these subsea, like high density flows. They travel down, just further down the slope. They still act under gravity, right? So they're going to flow down, and a lot of times these flows are confined to channels or submarine canyons, but they act under gravity, right? And density. So they're being pushed down. And so what happens is eventually that slide will stop moving. It'll reach a place where it kind of settles. And what happens is that you will get a separation of the sediments. So as the flow reaches, deeper into the ocean basin, it slows down, it loses energy, and those sediments begin to deposit. And with the Boma sequence, what's observed is that the coarse grains deposit first, followed by increasingly finer grains. So typically, your finer grains will come out of suspension first. The bigger grains, I'm sorry, the finer grains will come out of suspension last. The bigger grains, they're heavier. They need more energy to stay suspended. Bigger grains will come out of suspension first. They're heavier. They come out first. So if you think about um, if you've ever swam in a lake, you have a lot of fine grain material in lakes. You have silt, you have clay-sized grains. If you walk around and you kick up the bottom of the water, you're going to kick up that soil and it's going to stay in suspension for a while before it settles back down. You need much lower energy for for the fine grain sediment to settle, to deposit. In systems where you have moving water or wind, so fluid systems, sand is actually the most easily transported and deposited grain. Smaller grains like silt and sand they're harder to pick up. Like once they're at the bottom, once they've been deposited and they're at the base of a channel, they are harder to pick up because of um, the like attraction they have, and they'll like stick to each other. So they're a bit harder to pick up, but once you have a high enough flow and once they're actually, suspended, they will stay suspended. So your you basically can get a variety of sedimentary structures referred to as bed forms that are created by fluid systems and how they interact with the sediment. So that's going to be controlled by the grain sizes that are available, the flow, the velocity of the fluid system, so the velocity of the wind or the velocity of the water, is going to determine the bed form characteristics. Do you get plain beds? Do you get ripples? And so we'll give you a few examples in the next few slides. So plain beds is one that can be created in both lower flow regimes and upper flow regimes. They are created in low flow regimes, and they look a lot like bedding planes, just on a smaller scale. And what you see are flat, parallel layers that form as sandy sediment piles and moves on top of the layers below. Like I said, you can see them in upper flow regimes as well. They can be created by fast flowing fluids as well, and they can look very similar to, non-flowing systems like lakes. But the key difference is that they will show a parting lineation. So lineations are like lines that you can see, and what you see are slight alignments of the grains in rows and swaths that are caused by high sediment transport rates. And this would be a distinction that would tell you, oh, this was a fast flowing fluid that came through here. So with ripples, they are sometimes called ripple marks, ripple crossbeds, ripple cross laminations, but they refer to the same thing. They basically look like little dunes. The ridges and the undulations in the bed are created as the sediment grains pile up at the top of the bedding plane and then fall. So with the exception of dunes, which are a much larger scale, ripples are typically measured on the order of centimeters. And a lot of times, your ripples or your dunes at least will be, when we'll talk about dunes, are asymmetrical, right? Ripples can also be asymmetrical. And when you see asymmetrical ripples, that tells you that the flow direction was in one direction. When you see ripples that are symmetrical, that means that flow went back and forth. So there was an oscillation between flow in one direction and then in the other. And you get the creation of ripples that are symmetrical. Now, dunes, you can think of dunes as, much larger versions of ripples. And they have typical examples of or like textbook examples of cross bedding. So cross bedding happens when ripples or dunes pile on top of each other and they basically interrupt or cut into the underlying layers. So you'll get an accumulation and then an erosional surface, and then an accumulation and then erosion. And you basically see a sequence of accumulation and erosion and then new accumulation. And typically with dunes, you have accumulation of sediment on one side. So it's the sediment, the windward side. So as the air flows, the sediment along the windward surface, so facing the wind, the grains will accumulate there. And the angle of the windward side is typically shallower than the leeward side, which would be the downwind side. So what you have are sediment grains being pushed up, pushed up, pushed up, pushed up, and then you get to a certain angle that is reached by the sand grains where they won't go beyond a certain angle. And once you get to that point, the sediment will get pushed down this slope. And that continued process is actually how the whole dune itself migrates, because you just have the continual moving of that sand And as you continue to do that, the sand dune itself won't grow higher. It's limited by the angle that those grains can actually like come together and hold. So what happens is instead of the structure getting higher, the dune moves or migrates. There are some additional sedimentary structures that are discussed in the book. I'm skipping over them since this presentation is already well over an hour, and I want to get to depositional environments, which are an important part of interpreting sedimentary rocks. So what are depositional environments? These are places where sedimentary rocks form and accumulate. So we talked about stratigraphy, which is the study of the layering of sediment. The ultimate goal of stratigraphy is to understand the original depositional environment of those sediments, of those rock, and knowing where and how a particular sediment formed, how it was formed, helps a geologist understand past environments. Were there glaciers involved? Was it a gentle floodplain, a desert, a deep sea ocean floor? All of these things are very important for putting together a picture of the past. And more applicably, I guess I would say, as a petroleum geologist, this is also very important because if you understand the type of environment you're in, then you are better able to predict where potential reservoirs are located. You basically have three types of depositional environments. There are marine, terrestrial, and then transitional environments or, near shore kind of environments. So the first marine environment would be abyssal. Abyssal sedimentary rocks form on the abyssal plain. And this is the plain that encompasses relatively flat ocean floor. There are minor topographical features here, usually pretty small seafloor mounts. Most abyssal plains do not experience significant fluid movement. Like once you're at the ocean bottom, there's not a lot going on. I mean, you get flow of water and you can get certain features called contourites. So you can kind of think of them as like ripples on the ocean floor. But basically, the sedimentary rocks that form here are going to be very fine-grained rocks. So think, shales. One way that you can get a larger grained material on the abyssal plain is through submarine fans and turbidite deposits. You can get these submarine fans that occur at the base of large river systems, and they're usually initiated or carved out during times of lower sea level where you have like a strong river current that carves out these submarines once that river meets the ocean. And so you can get the accumulation of sediment there. And you can also get, those turbidite deposits that come off of the slope and go down into the abyssal plain. Now moving closer to the surface, your lower shore face is below the normal depth of wave agitation. So the sediment is not really subjected to daily removal and deposition. These sediment layers are typically pretty finely laminated or finely deposited, meaning that the layers that they're deposited in are rather thin. Your lower shore face beds they can be affected by larger waves though. The upper shore face environment or in setting contains sediments that are within the normal zone of wave action but still submerged below the beach environment. And these sediments usually consist of very well sorted fine sand. The main sedimentary structure here is going to be planar bedding, which is consistent with the lower part of the upper flow regime. Your transitional coastline environments are zones that are more complex. There are complex interactions that are caused by the ocean water hitting the land, the sediment preservation here, it can vary. So these environments, because deposition occurs on the continental shelf and under the water, you can have high preservation. But if you have decreasing or subsiding sea levels, then you can have, all of the accumulated material be eroded away. And there's actually a subdiscipline of geology, and subdiscipline of stratigraphy even, called sequence stratigraphy, which looks at the shoreline depositional environment, and this sequence of deposition and how it basically changes with rising and falling sea levels. The littoral zone, also known as the beach, has highly weathered, homogeneous, well-sorted sand grains that are, well, in most cases, made of quartz. And in this environment, you have you don't really have sedimentary structures due to the constant bombardment of waves, and sediment being moved around in a lot of different ways. So you can get dunes that develop, but not in the area where it's affected by high tide and low tide, like basically where you have the water moving. Tidal flats are also called mud flats. These are sedimentary environments that they are found near coastlines. They are regularly flooded, but they are also drained. Like they also drain into the ocean. These tidal flats can be, pretty large areas, and the type of sediment you find here is typically fine grained, especially in like the interior parts. You can also get coarser sands in there as well. I mean, these tidal flats are typically pretty proximal to beach environments, so you will find sands there as well. When we talk about reefs in terms of depositional environments, uh, we are referring to what you imagine a reef would be, a coral reef. And what defines a coral reef would be, or a reef, would be an elevated surface that is like located within or on top of the continental shelf, and it is located oceanward, meaning not toward the land but toward the ocean, but it is also separate from the beach. Now, unlike the reef that you're probably thinking of, which are natural structures, you can also have man-made reefs, and these can form from, structures that are left behind in the ocean that we leave behind, be it a drilling rig or a sunken ship or something like that. Lagoons are similar to tidal flats in some respects. They are typically, in closer proximity to coastal environments. But one big difference with lagoons is that these small bodies of seawater they tend to be more isolated than a tidal flat would be. And so they can be isolated by geographic features like a reef or a barrier island. They tend to be more protected from the action of tides and currents and waves. And because of this, the sediments that you get in lagoons tend to be very fine grained. Around lagoons where you can have um, evaporation, like you can have an influx of water that gets evaporated, you can create what are called salt flats or sapkas. And you can also have sand dune fields that develop at or above the high tide line around lagoons. And another thing, lagoons and estuaries are bodies of water that still have fresh water. So estuaries tend to be areas where you have freshwater and saltwater mixing. Lagoons tend to be saltwater, but like estuaries, lagoons are areas or ecosystems that have a lot of biological activity. So you tend to see a lot of biodiversity in and around lagoons. One of my favorite sedimentary structures, geological features, are deltas. They are the structures that form where rivers enter a body of water that typically has a lower flow velocity. So typically when rivers empty into lakes or oceans is where you get the development of deltas. And there are three basic shapes. You can have a river-dominated deltas, you can have wave-dominated deltas, or tide-dominated deltas. The velocity of the water flow is dependent on the riverbed slope or the gradient of the river. So that base of the channel, whatever slope that is going to have an impact on the water flow, which becomes shallower and shallower as the river descends from the mountains. And so imagine, a river on a higher slope, the velocity is going much faster, and then as you reach flatter land, that velocity is going to slow down. So at the point where a river enters an ocean or a lake, its slope angle is, close to zero. It's at sea level. And so the flow velocity will quickly drop. And what this means is that the sediment, or a lot of the sediment that was suspended in that flow, will drop out of suspension, meaning that the sediment will be deposited. And anything basically that's left in suspension will drop, whether it's coarse grain sediment to fine grain sand to even mud, will form and start to build that delta, because that's where that flow rate is changing, and so that's where the delta starts to build. If you look at the picture of the Nile here, which is the one that's on the slide, the Nile River Delta, this is an example of a wave-dominated delta. And what that means is that the kind of the outer extent, the outer reach of that delta is shaped by wave action. So if you notice the outer shape here, let me get my pointer here, it's smoother. And so your wave-dominated deltas generally have smooth coastlines and beach kind of ridges on the land that represent, the previous coastlines. If you look in the book or Google it, the Mississippi River Delta is an example of a river-dominated delta. And this type is dominated by levees, natural levees along the river. And its distributaries as well, they confine the flow. So basically, as the delta builds out, it's also building like a channel for itself. So its distributaries also confine the flow, forming a shape that looks a lot like a bird foot, and that's where the name, the bird foot delta, that's where it gets its name, because it kind of looks like a bird foot. And then the third type is a tide-dominated delta, which is, like it sounds, it's dominated by tidal currents. And what happens here, so an example of this would be the Ganges River Delta. During flood stages, when rivers have a lot of water available, it develops distributaries that are separated by sandbars and sand ridges. And so the tidal delta of the Ganges River is actually the largest delta in the world. And lastly, we have terrestrial depositional environments. And these are still dominated by the movement of water, but they're not happening in the marine setting or near a marine setting. So the first one we'll talk about is a fluvial system. So fluvial, the term fluvial refers to rivers. So fluvial systems are formed by water flowing in channels over the land. They generally come in two varieties, two main types. You have a meandering river or a braided river. In a meandering river or a meandering stream, the flow carries sediment grains through a single channel that meanders, basically wanders back and forth. The river will kind of carve a path of least resistance. So, that's why it doesn't always it doesn't really look like it makes sense. Why does this river snake like this? It's the river kind of found a way to flow not only down slope but down a path of least resistance. So oftentimes that means that the river takes on a shape that is very meandering. With meandering rivers, when you have floods, so floods will happen regularly. The river will exceed its banks, and when that happens, that's when you get deposition near the river. And typically, the sediment that's left behind from this sort of scenario they're mostly fine grained material. So if you think back on recent floods, like even the big flash floods that happened of the Guadalupe River, when the water came back down, when the water levels came back down, what was left behind was mud. That was all fine grained material. So that's what gets left behind from these types of river systems when they go over their banks, and then eventually the water will go back down to within its banks, and that's the sediment that gets left behind. Then you have the braided fluvial systems, and braided fluvial systems consist or contain coarser sediment grains. So here you almost have like a supply problem. Like you have a lot more sediment that is available to be moved around, but not enough water to move it. And so you see a much broader range of grain sizes, and you tend to see larger grains as well. This type of river system, they form complicated series of like interweaving channels that it's really hard to tell where one channel starts and ends. You just have to look at it as like all one system. And here's what that looks like, a braided fluvial system. Now, an alluvial system is a lot like a delta, except you don't have as much water. So alluvial systems are, terrestrial depositional environments, and they are controlled by water, but in these systems, the presence of water is sparse and intermittent. So it doesn't always have a constant flow of water. And these types of deposits are most common in arid places and in places that have very little soil development. But you do see a shape that like a fan kind of cone shape of sediment that accumulates. That is, similar to deltas. There's certain kinds of deltas. And alluvial sediments, they are usually very close to like high topographic areas. So you typically see them at like the base of a mountain or the base of like, an elevated area. And so because of this, you get very poorly sorted, coarse-grained material here. You don't have a lot of transportation of these sediments. They don't go very far. The water hasn't carried them very far. They're kind of dumped kind of close to their source. So because of that, they're not going to be, well-rounded or well sorted. Lake systems and the deposits associated with lake systems are called lacustrine. And some of these some lacustrine systems can be similar to marine deposits. Um, Lacustrine deposits, they are found in lakes in a wide variety of locations because you can have lakes form for a wide variety of reasons. You can have a tectonic basin, maybe from rifting, or just extensional features, like if the continent experiences thinning, crustal thinning, you can get uh, lakes that form. You can also have lakes that form because of volcanic activity, so a volcanic caldera. You can have lakes that form from glacial erosion. Uh, you can have an oxbow lake, and these are lakes that form when a meandering stream kind of gets pinched off, like it meanders so much and creates like such a big loop that eventually the river kind of finds a path of even like less resistance and will kind of cut off a certain part of the lake, or I'm sorry, a part will cut off a part of the river, and that part that's cut off becomes a lake, and that's known as Oxbow Lake. So there are a lot of different ways that lakes can form, but in general, lakes will have an influx of water, an outflux of water, but the flow of water tends to be quite low, and because of that, um, you can get the deposition of very fine grained material, and that's typically what is associated with lacustrine sediments. Very fine grained, thinly laminated, meaning that the beds that are deposited, the sedimentary beds that are deposited, are very thin. Um, and there are, you know, evidence in the geologic record of when previous lakes have dried out, which can happen, and that has a specific name. It's called a playa when you have a lake that basically dried up. Um, but here with playas are a little bit different because you have to have evaporate minerals in playas as well as the normal lake deposits. Aeolian basically just means like windblown sediment, and when you think of Aeolian, you basically the main features you get are dunes and more dunes, variations of dunes. You have, your traditional common dune, which looks like this here. And so this would be so this is like a map view, and this would be a side view, like a cross section. Your sand grains travel this way, and then once they reach a point at which they can no longer climb, they fall. So we call this the Stoss side and the Lee side. So Stoss, Lee. And they climb, 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 and then fall. And so this side here tends to have a greater, steeper slope than this side here. Now, because wind doesn't always blow in the same direction all the time, you can get a variety of dune formations that can form when you have, varying winds at different times. Okay, the last depositional environment is glacial. Glacial sedimentation is very diverse, very messy. It contains sediments that are very poorly sorted, and it's because of the nature of a glacier. They are very strong, so they can carry very large class pretty far. So glaciers can pick up big pieces of rock and carry it pretty far. And once it is being carried, at least within certain parts of the glacier, those clasts aren't necessarily going to be like abrade and break down, if they're just being like passively carried along within the glacier. So the glacier itself can preserve really large chunks of rock, but at the same time, as the glacier is moving, like the boundaries where the glacier is coming into contact with the rock and it's carrying around rock, it can pulverize other rocks. So while on one area, like for example in this picture, you see, these big chunks here being carried around, but like at the base of this glacier and on the sides of this glacier, that glacier is grinding up the rocks and it's creating very fine sediment as well. So ultimately, when this glacier retreats, it's going to leave behind um, sediments that are very widely mixed. You're going to have, just poorly sorted angular sediment as well as, very fine um, pulverized rock flour, and everything in between. And the very last thing we'll talk about is the term facies or lithofacies, which basically refers to all of the characteristics of a rock that reflect the environment where it came from. So a facies includes the rock's composition, its grain size, its texture, fossils, color, like any of the features that can be used to determine its depositional environment. We call that the facies. And why does it matter? We use facies to interpret depositional environments, which we've discussed the importance of that. Different environments create different facies types, like a marine facies or a deltaic facies or fluvial facies. So you can think of facies as like a fingerprint of an environment that is recorded in the rock. I know this video is so long, and I'm really sorry. This is such a long chapter, and I feel like I could have spent more time talking about certain things. But as always, email me if you have questions. I'm happy to help. We can set up a phone call or a video chat if there's anything you need help with or want clarification on.